10 years. Okay, it really depends on what you're doing. What I'm going to be showing you is you can use it on a monthly basis versus 10 years out. And when I say that, I could probably get away with using an average or a weighted moving average over 3 months, but I'm not going to get away with it over a 10-year planning horizon in that regard. You've got to have a very sophisticated model. If you're going out 10 years, you're really going into simulation at that point, which is really complex. Excel does it, but it's fairly complex. You got to look for the data patterns. If you have changing data patterns, particularly trend and/or seasonal data patterns, your forecast will always lag. By that I mean if it's a decreasing trend, you're going to overestimate. If it's increasing, you're going to underestimate. You're going to have that a little bit. So it becomes more important to use a more complex model, like what I'm going to show you when that occurs. All right, let me switch gears. Let me sit down. And let's get into something more than you just looking at PowerPoint. There we go. Now we're getting something. All right. These are 3 basic forecasting models, and I'm going to give you this file. And you can put your own data in there. It looks complex, but what you have to do with it is simply get your actuals, and you would have to know what your forecast was from your budgets in that. And so when I said the periods, the actual value, and then the actual forecast is all the information that you enter, okay? Everything else is calculated in this process. So all of this information over here, your error, your absolute error, your squared error, your absolute percent error are all calculated for you, okay? And what it's doing in a trend is placing, you've seen linear, simple linear regression, where it basically plots a line through the data. So if you've got data points up around that line up there, that line through there would be the best fit line from a linear regression standpoint that reduces the squared error of the random variation, right? That's all this process is doing in here. So what it's doing is it's taking the error. So for instance, the error here is your forecast of 5675 versus an actual of 57. And so 57 versus 7,900, and so forth. It takes this and it gets rid of the negatives because negatives skew the process, makes them absolute, squares those, to add all this up to an MSE, and then gets you the percent error. And the percent error is simply your actual, or the absolute error divided by the actual value times 100. Okay, that's your percent. So what that percent error is saying is that we had an actual value here of 5750. We had an error of 375, because the 375 comes from your trend forecast versus your actual. That's where that comes from, okay? So the model was saying 6125, we actually hit 5720 in this year. Make sense? In the forecast. And so the percent error, it's off by 6.5%, is basically what it's saying, okay? So the goal in these is to reduce, remember you see from the article, your MAD, your MSE, and your MAPE, right? The goal is to reduce these, in particular, the MAPE, to as low as possible, okay? And this model runs by virtue of the regression, intercept, and the negative slope. So that's your regression line. If you look down here, basically a regression line. Make sense so far? Okay. So the problem with this is when you look at it graphically, from a linear trend standpoint, what's going on in ninth ortho? The way I've set this data. This is the actual data points here. So we went for a few years where we were markedly increasing, and then because of the pressures of outpatient surgery, what happened? Started falling off, right? So we actually had a change in trend. That is probably the most complex process you can do, is come over the hill and try to figure out where to go from there, based on historical data. So when you look at it graphically, you see this line here, that's the regression line in these data plots, right? This is the same effective regression line, this green line, regression line here. So these were your actual census points over the planning period or over the historical look of these years. And these were your forecasts over those years. What happened to the forecast versus the actual? Well, what happened here? This is your forecast. Go back and look at your points. What was happening? This was probably a naive forecast or a simple average forecast. So we see this kept going up, right? So we kept going up. And then what year did we go? In year 4, we started to see a decline, 2015, even though they kept forecasting up, right? The model is even saying come down. But what's happened to the model even here, because it's linear? We've had this is the projected drop-off. I did the projection based on current performance to the end of this year. This is where they're expected to be at the end of this year, based on current performance through April 30th. So even the model is overestimating this. And it's lagging because it's going to take some time for the model to adjust and begin to tilt down to follow this over the hill because of the impact of these early data points in a regression fashion. Does that make sense?
So if the patient doesn't hit midnight, they don't count as a patient day, right? Okay, so I know what they're doing. They're admitting patients post-operatively outpatient. They're getting 1 PT, some pain meds, and being discharged by 8 p.m.
Yeah, I want to show you that in the second half of the day. That's why I gave you guys your admit and discharges.
Yeah.
So you can calculate when you got a length of stay of less than 24 hours. And their average length of stay actually is 2.78 days. But they do have those patients where they are in and out.
It's 6 hours,
Yeah.
and 6 hours.
Yep.
So should they even go to the floor?
Well, that's a different strategy.
That's a whole other fight right there.
Yeah.
So does this make sense and why this model is really not as effective? Because it's impacting, the reason this line is not running like this is because it's taking into account the fact that you were running up the hill in actual values for a period of time. So when it's trying to fit a best fit line, it's limited in its ability to respond to this by virtue of this. Does that make sense? Okay, so you have here an error rate of 4.36% overall. And that's your mean absolute error percentage rate. Okay? So overall, this model has an error rate and it's a prediction ability of 4.36%. Does that sound like a lot? It can be. It can be. Okay, let's go to the same data on an exponential forecast. And I'm cheating a little bit, and I'll tell you why in a minute. Okay? Now this is where I talk about the smoothing process, right? Where it's taken into account which periods it looks at. So this is your smoothing constant here. It's called an alpha. This is the way it's termed in this vernacular. And it's set to look about halfway back. That's where that 0.5 comes in. So if I've got 8 years of data there, roughly, it's set to look back and be most predictive somewhere back in here. That's why, and again, get that off there. This is your actual census. This was the forecast, and this is the model recommended forecast. That's why the model has started to follow it more closely than the trend did, right? It's turned, but it's still lagging. It's still up higher in its projection than what the actual is. Because if we continue on the same trajectory for 2019, we're probably going to be somewhere down in here, right? So it's still lagging. And that's because it's looking back here. But I told you you can change that smoothing constant, right? So there is a function in Excel called Solver. It's an add-on, and I can show you how to add it to your Excel package, okay? And what I do with Solver is I want the model to minimize the error rate based on changing the alpha. But I don't know, I could sit here and play with this alpha all day long. And I could change it to 0.6, and you'll see the model move down, right? Or I could say, well, I really believe it's a 0.2, and you'll see the model move up, right? But we want that model as close to reality as possible because we're trying to predict what's going to happen next year in 2019, right? So what I do, and you'll notice what happened to the error rate. It went exponentially up. This is where the power of this comes into play. So what I can do is go back to this number here, and I already have this set, and I can show you how to set this in Excel. I go to Data, and I have an add-on over here under Analyze called Solver. So you can basically tell Solver to do a what-if scenario, okay? So I have Solver set to minimize B22, or minimize, I'm sorry, I22, that's the set objective. I22 is your mate, right here, where I have the green arrows around, right? By changing the alpha, which is the B22, right? And I have a constraint set because you can never have a smoothing coefficient greater than 1 in this process, okay? So watch what happens when I do this, and I say, okay, solve this and tell me what the best fit is. So I say, keep the solver solution, yes. What did my alpha change to? It went to a 1. What did my mate change to? 3.4. What did my green line do? It's really starting to fall off because now it's paying attention to what's going on here because this is where we really have the changing trend, okay? But does it still lag? Is it still going to be off? Because we said probably we're looking at being down here somewhere. Okay, so this is where judgment comes into play and what you're seeing too, measuring the qualitative and quantitative side of this. But we're closer, right? So there's a process called double sequential or trend adjusted exponential forecasting that takes into account an additional data. This is a smoothing constant, right? This looks at which period and emphasizes kind of where in the chart it's going to look at the most of the data, right? In the history of what we're looking at. This is trend. This gives you ability to adjust for how rapidly the demand on that unit is de-accelerating or decreasing or increasing. So that slope of that line right here, it gets to take into account. I'm adjusting that, okay? And I can play with those numbers again all day long, but, and you can see, even as I have it set right now, I have the trend on here from the previous, right? And I have this one. This purple line is this forecast, the most complex one. It's even further down right now, isn't it? Right? So what happens whenever I optimize those two, the alpha and the beta? I do the same thing. I go to solver. I already have them set. They both have to be set to less than 1. And I minimize the mate. Now what? 2.78% error. What's my alpha? 1 again. What's my trend coefficient or my beta? Almost 1. So it is really because of how rapidly this unit is declining in census or in patient days is really paying attention, it's taking into account the other years, but is really paying attention to those last few periods. So what did I tell you we thought was gonna happen in year 19 down here? Did I say it's gonna probably come down here somewhere? Where's my forecast? They're gonna just about meet, aren't they? Is that a little more predictive? This is what we do with forecasting. There's nothing magical about this from y'all's standpoint. I'm gonna give you this tool. All you do is just adjust the period you're looking at, and then choose which one gives you the most accuracy, and use Solver, and I'll help you set up Solver, because it's a very simple process, to determine the combination that's gonna get your prediction as close to where you think your actual is gonna go. Because right now, the prediction is 5484, right? What is I'm saying about my performance at the end of 2018? 5478, right? So we're pretty close in terms of where we think this is going to go in 2019. Make sense? Pretty interesting? This is where you got to go in terms of overall, when we do forecasting, we start, what's going to happen we think next year? Okay, what's the big number we have to start with that gets our budget started? And it's that annualized number. And what method do we use to try to figure out what's the best possible scenario that that number is going to be based on what's happened in the past? Okay? So that's our starting point. What time is it? Yep. So we're going to take a break. And again, I apologize. I cannot control the government and the Employment Commission. And we'll make this as short as possible. We'll let you guys kind of breathe on this for a second. I'll leave this up here. Feel free to look at it. We'll ask your questions. We're going to spend the last amount of time going through the actual Excel file. Because now we've got our number for 2019. But we've got to kind of determine what's happening on a monthly trend basis, a daily trend basis, and an hourly trend basis from what? Because you get the nail on the head about same-day admit discharges. Right? This data only takes in, the first half of your data only takes in midnight census. It doesn't tell you anything about admit discharge workload, does it? So I'm going to tell you how to graph that so you can tell when your highest hours of work are related to admits and discharges are, so you can kind of plan for that beyond your base budget. So that's kind of our next step once I take care of this real quick. All right? Make sense? Think about your questions. And I'll be happy to answer any questions you got on this once we come back. And then we'll go from there. Okay?
So do we need our file that you sent us, or you're gonna do ninth?
I'm going to do
ortho up
ninth
there?
ortho on here, but you're going to follow on your file. Okay? So you can, as we do this, build it yourself. And then I'm going to have a homework assignment for you to take that 2018 data and do what we do in class on that 2018, that month of 2018 data on your own. Repeat it and report out on it next time. Okay?
For your